Well, here we go again, and this time we're starting to look at our gas laws. We looked at kinetic molecular theory in explaining how gases behave based on observation and their movement, size between particles and all those kinds of things. Now we're going to start to look at some of the equations that we're going to use to help us mathematically derive things to do with the gases. And the first thing that we're going to do is Boyle's Law. Hopefully you're watching these videos after we've done the small demos and pracs in class, and these will make a little bit more sense and they'll relate back to those activities that you did. But the first one we're going to do is look at Boyle's Law. So all the gas laws essentially allow us to define gases according to those four main constants we were talking about. So temperature, pressure, volume, and the amount of gas that we have in mole. So these four things, okay, are the main ones that we were talking about in terms of we need to know each one of these variables in order to define our gas. So the gas laws came about over a fairly long period of time, from the 17th century forward, and they were all derived from main experiments by a number of different scientists. The three that we tend to look at the most is Robert Boyle, Charles, and Avogadro. So let's get started. Boyle's law essentially is looking at the relationship between volume and pressure of a gas. We're looking at our variables for V and P. These are looked at in isolation. So we always need to, when we're looking at a gas, know what's being kept constant and what's changing. So in this case, because our volume and pressure are the ones that are going to be able to be changed, we need to have a constant amount of gas. So we've got a constant number of mole. Okay, so we're not adding in or taking away gas from the sample. The amount of gas we have stays the same all the time. And we also have to have constant temperature in this case. Okay, so we're keeping T constant. There's no change in temperature. And then in this case, we'll be able to observe the overall proportionality between volume and pressure. If we have a look at this interactive, we can start to see what that will look like. You'll notice in this case we've already got the pressure set to 1 atmosphere. The temperature is 325 Kelvin. We have a volume of 800 litres. We already have some gas in our container. We're not going to change the amount, so we're not going to push the plunger here and add more or less. We're not going to change the temperature. Okay, so what we're going to do now is increase or decrease our volume and see what happens. So as we decrease our volume, we can see that our pressure gauge here increases. Okay, if we increase our volume again, we will see that our pressure decreases. So this is the same as the experiment that you should have looked at when we push in a syringe or even a bicycle pump. This is a good example of Boyle's law. As we decrease the volume by pushing in the plunger, we see an increase in pressure. So with a bicycle pump, we see the increase of pressure and that forces the air into our tire and we can feel that resistance as we go. So this is similar to the syringes that you looked at in class. As we push the plunger in, we are decreasing the volume and we feel an increase in pressure pushing back against us, remembering that pressure is simply a way for us to define the number of collisions between the gas particles and the walls of the container. So what we're feeling when we push this in is the gas actually pushing back against that and resisting that change. Okay, if we then pull the plunger out, we will notice that there is a decrease in the pressure. If we plot this, if we do a series of experiments where we keep our temperature and the amount of gas the same and we just change our volume and record the pressure, we will be able to plot this in a graph of pressure versus volume. And what we will see is this inverse relationship here. Okay, so what we're seeing is that pressure, as we increase the pressure, our volume goes down. If we decrease the pressure, our volume will go up. So they are inversely proportional to each other. When we look at this using other graphs, this one on the left here, we are plotting pressure versus volume. So we see that negative relationship here, this inverse relationship here, where it's a 1/x relationship. If we actually take this and we plot, this is our pressure versus volume. If we actually plot this with 1/volume, what we will see is that this turns into a straight line. Okay, so it is proportional to the inverse. Okay, so if we just plot directly pressure and volume, we get this 1/x relationship. If we actually then plot that versus the 1/, what we get is this straight line showing that we have that proportionality for those two variables. If what we actually do then is if we take a plot of the pressure times the volume versus the volume, we will see that it's actually a straight line. Okay, and that's because if our volume is proportional to 1/p, or P is proportional to 1/v, what we get is that being equal to a constant. So if we multiply the pressure times the volume, it should equal a constant value, and we see that by this horizontal line where we're not seeing a change. Okay, that's giving us that constant value. The main ones that you need to be able to identify is this pressure over volume with the 1/x relationship for Boyle's law, and the pressure versus 1/volume giving us the linear relationship. But just remembering that they are an inversely proportional relationship. As one goes up, the other goes down. So if we define this mathematically, okay, so we know for a fixed mass of gas or amount of mole of gas at constant temperature, the volume is inversely proportional to the pressure of the gas, which means that we end up with this relationship here. If we multiply, we saw on the previous slide, if we multiply pressure times volume, it equals a constant. Okay, if we take this from an initial condition to a final condition, what we now see is that this mathematical relationship holds here. P1 times V1, so this is our initial condition, equals P2 times V2. You should recognize this as being very similar as our C1 times V1 is equal to C2 times V2 that we saw for our dilution equation. Same kind of proportionality, which means that in this case, we don't have to worry about units for pressure and volume. As long as they are on the same on both sides of the equation, it doesn't matter if our pressure is given as atmospheres, pascals, millimeters of mercury. As long as we're looking for the same value on both sides, it won't matter and we don't need to convert. Same with our volume. Okay, so now that we have defined Boyle's law, let's have a look at some questions. These ones will always involve an initial and a final set of conditions. So let's have a look. In this first one, we've got an observation balloon and we're told it is filled with helium gas to a volume of 40 decimeters cubed. So we've got a volume, which is going to be V1, and then we're given a pressure of 100 pascals. So this is going to be P1. We're asked to calculate the volume when the balloon rises to an altitude where the pressure is 20 pascals. So we have a P2 and V2 is what we are going to be looking for. So we have identified each of our knowns and our unknown. Boyle's law equation states P1 V1 is equal to P2 V2. And this time we've got our initial balloon at 40 decimeters cubed. Okay, it's going to rise to an altitude at a pressure of 100 pascals. As we get further away from the Earth's surface, our pressure decreases, so we will now have our balloon will be at 20 pascals. And we know that it's an inversely proportional relationship. So if our pressure has gone down, we can expect the volume to increase, but we need to find out by how much. Sorry, that screen is flicking. Let's see if we can stop that. So what we're going to do now is we're going to solve for V2. So we're going to rearrange our equation. P1 V1 over P2, and we're going to substitute in. So P1 was 100 pascals. We're going to multiply that by 40 decimeters cubed all over our 20 pascals here. So we can get rid of these. We get 400 divided by 2. Okay, 400 divided by 2, which is 200, and our unit, okay, this is a volume, remember, our unit, we started with decimeters cubed, so this one will be decimeters cubed as well. Okay, so, and if you have a look at this, our pressure went down by 1/5, and our volume increased by 5 times, which makes sense for the inverse proportionality. So let's look at another couple of questions and get a bit more practice with this, and then we're done. These ones we're looking at this time a sample of air in a syringe, so similar situation to when we investigated Boyle's Law in the classroom. We have a syringe. It has a volume of 120 centimeters cubed, so this time this is V1, remembering we don't have to worry about units because we're using this P1 V1 P2 V2 as long as we know what the units are at the end. And we have a pressure of 100,000 pascals, which is my P1. Temperature is constant, the amount of gas in the syringe will be constant, and we are looking for V2 for each of these different pressures. In this case, we can see straight away, if we have a look here, we have doubled the pressure. Because we've doubled the pressure, as we saw last time, if we've doubled the pressure, we will halve the volume. So this one's a really nice and easy one, which means our volume must equal 60 centimeters cubed. You can plug it into the equation and check if I'm right, but you should find that because we have doubled the pressure, we will halve the volume. Okay, so we've done times 2 for the pressure and the inverse of that for the volume, so it's 1/2. Let's look at this one. Again, P1 V1 equals P2 V2. For all of these, we are looking for V2. So we're going to P1 V1 over P2. In this case, 120 times 100,000 all over 45,000. I'll leave you guys to do this to work out your final answers. Of course, in this case, we are looking for a volume, and it's going to be in centimeters cubed, your final volume. Okay, and then this third one I will leave you to practice on your own, just pointing out here that we have kilopascals. So if we had to convert, we would just multiply by 1,000 to get it to pascals. However, because we're using this P1 V1 equals P2 V2 relationship, no conversions are necessary. If they're the same on both sides. Okay, but if we have a look, we've already been given our P1, and we can see here P1 is in pascals, P2 is in kilopascals, so we will need to do a conversion. You can convert to pascals or kilopascals, either one will be okay. I would probably convert to pascals, so in this case it would be 64,000 pascals for your P2. Okay, substitute those in, see how you go with that practice on your own. And those are pretty much the straightforward Boyle's questions. We always have an initial set of conditions, a final set of conditions, and we're just always looking for one value, being either our initial or final pressure or volume, depending on what the question is asking for. So this is essentially what we need to know with Boyle's law. You should be able to, after this, state the relationship between the volume and pressure of a gas, remembering that for Boyle's law, temperature and the amount of gas must remain constant.
Okay, so this means that this one is simply saying that pressure is, whoops, sorry about that, pressure is proportional to 1 over V, or they're inversely proportional. Recognize Boyle's law when graphed graphically, so we have these one and this one. If this is pressure and volume, and this is pressure and 1 over volume, okay, and then the mathematical formula P1 V1 equals P2 V2. And there we have it. So next up, we will be looking at Charles's law, which is the relationship between temperature and volume.